Hello, this is Dr. Eddie Morgan over at Clovis East High School. I want to walk through the Unit 8 review with you, and hopefully this will help you for the upcoming test. The first question is, what is a rigid motion? A rigid motion is a transformation in the plane that preserves distance and angle measures. That simply means that the size, the length, and the angles don't change distance. The sides are the same length and the angles are the same measure. We've been studying three types of rigid motion: a translation, a rotation, and even a reflection. And in each of those cases, it doesn't change size. Think of a rigid motion as having like a box or something it's metal or it's wood. It stays the size. You can move it around, you can turn it upside down, you can throw it across the room, but it stays the same size. And that's what a rigid motion translation is. Problem number 2 asks us to name the transformation that's occurring between those two trapezoids. If you notice the blue lines that I've drawn, you can see that the figure is simply being rotated counterclockwise 90 degrees. That's the transformation that's occurring. It's a rotation. Is it a rigid motion? Yes. You'll notice that the two shapes have the same size, the sides are the same length, and the angles are the same measure. So that is considered a rigid motion. You want to remember this phrase: it preserves distance and angle measures. You can use that phrase at least twice on the test to answer questions about, does it change size, is it rigid motion? So try to remember that phrase: it preserves distance and angle measures. Problems 3 through 8 ask us to describe the transformation represented by the coordinate notation. If you notice the first one, xy becomes x minus y. So if you think about that on a scale, what's happening is that the x stays the same, but the y flips. And so this is what would be if we're crossing the x-axis. You notice like point A is negative 3, but A prime is also negative 3. All that happens is the y flips across the x-axis. So that is a reflection across the x-axis. A reflection across the y-axis, interestingly, the y stays the same, but the x would change. In number 4, you notice that x stays the same, but y goes down 1. Y negative 1 means I'm going to go down 1. So what I have is a translation down 1. You notice the triangle just shifts down 1. The x's stay the same, but the y's go down 1. On the next one, we do the same thing, but with the x. Notice the x changes by adding 2, which means I'm going to shift 2 to the right, but y stays the same. So this is a shift of the triangle 2 to the right. In number 6, we have an interesting thing where x and y actually change places and one becomes negative. This is actually the rotation 90 degrees clockwise. If you were to look at point A in the original triangle is 2, 3, but then when you rotate it, it becomes negative 3, 2. And that's the nature of the negative yx. By the way, if you get y negative x, that's a full 270 or 90 degrees going the other direction. Number 7 is kind of easy to remember. You notice that both x and y both become opposites. And that's kind of like reflecting it over the x-axis and then reflecting it over the y. What you have here is this is the total counterclockwise. If you take it and go 180 degrees, you'll see that 2, 3 becomes negative 2, negative 3. And so the negative x, negative y is a 180 degree. And finally, number 8 is just a translation where we have x minus 2, which means I go 2 to the left, y plus 3, which means I go 3 up, and so it looks kind of like that: 2 to the left and 3 up. Problem 9 asks us to name 3 transformations that will map the shape onto itself. There's a lot of them here because this is a square. I think on the test you'll get a rectangle, so there won't be quite as many, but a square, there's lots of ways you can turn and reflect and move this to get the same thing. First thing I notice is that I can simply do a rotation. If I rotate this square 90 degrees, I still have a square. In fact, I can do it again. I can rotate it 180 degrees and get a square, or 270 3/4 and get a square, or I could go all the way around 360 and come back to where I was. So you can do a rotation. Likewise, I can do some reflections. If I choose the x-axis, notice I can flip. I'm just turning the square upside down. I get the same thing. I can also do it on the y-axis, left to right, and just flip it from one side to the other, and then even diagonally. unique because it's a square. Notice if I flip it diagonally, I still get a square, and I can use the y equal x line. I can also use the y equal minus x line. So there's a lot of ways that I can map this one onto itself. It's unique because it's a square. The more different the shape is, the less of these are available. Number 10 says that triangle ABC has been rotated 90 degrees clockwise about the origin. Name all of the sides, angles, and sides. Well, so this is what I've got. I've got a 90-degree rotation. First thing I notice, if I want to just check myself, I'm just going to notice that when I shift it, A becomes T, B shifts over to R, and C shifts over to 0. If you can ever write this triangle ABC maps on a triangle TRO, these problems become very easy, because you can actually look at these three letters and compare the other three letters and look where they're placed and find your answers. For example, A matches angle T. They're both the first letter in the triangles here, if I've done it right. B becomes R and C becomes O. Okay? Or you can just look at the diagram and see how did they go there. And then likewise, using these, you can put all the segments together, because obviously AB are the first two letters in the triangle, TR are the first two letters in the second triangle. Likewise, BC and RO, and then CA and OT. So just a note in helping you, if you can set up this first statement, triangle ABC maps onto triangle TRO in the beginning, you can actually answer all the other 6 just from looking at that diagram. In problem 11, we're asked to look at the quadrilateral play, PLAY, and it says it's translated up 5 units and left 8 units. What are the coordinates of P? Well, if I look here and just P and just use it, if I go up 5 and over 8, you see it's off the graph. So I either need a bigger piece of graph paper, or I may just want to use the coordinate notation. Notice here in the coordinate notation that up is the y-axis, so it's going to be y plus 5. Left 8 means x minus 8. So if I put in my point here, -3, 0, and so -3 minus 8 and 0 plus 5, I'll end up with that P prime is -11, 5, which looks appropriate even though I can't see it on my graph. In the next one, number 12, it says if play is reflected across the y-axis, what are the coordinates of L prime and Y prime? Well, let's draw the y-axis. It looks like that. And so I'm going to reflect. If I look at point L first, it goes over 1 to the y-axis, so I go 1 more, so that's going to be my point there. It looks like 1, -5. If we check it out, a reflection says that the x flips, but the y stays the same, just like our diagram shows. So -1, 5, if you take the opposite of -1, you end up with 1, -5, which matches what we see on our graph. We look at y prime's on the right side, so if I go back 5 to the y-axis and then 5 over the other side, you see I'm going to be at -5, 1. Let's check it out with our coordinate notation. So 5, -1, take the x and take the opposite, and we end up with -5, 1, which matches what we see on the graph. Problem 13 says that if our figure play is rotated 90 degrees counterclockwise about the origin, what are the coordinates of A prime and L prime? You could do this with patty paper. You could set your patty paper down, mark your figure, put a cross through the origin, and then put your pencil on the origin and turn your paper 90 degrees and try to figure it out. I find it just as easy to use the formula that xy becomes -yx. Notice the x and the y change places, and then the first coordinate becomes the opposite. So if I put in the point A, 4, -5, first thing I do, switch them, -5, 4, and then the opposite of -5 is +5, so A prime would be 5, 4. For L, same thing. L is -1, -5, so first switch them, -5, -1, then the opposite of the first one, -5, is +5, and the answer is 5, -1. Problem 14 asks us to, interesting question, it wants us to find the slope of P prime Y prime if it's reflected across the x-axis. You might look at PY right now and realize it goes down 1 and over 8, so the slope is -1/8. But what happens if I reflect that across the x-axis? Well, let's find out what P prime and Y prime are. P, by the way, is -3, 0. Notice that it's actually on the x-axis, so it doesn't change when you reflect it. On the other hand, y prime, remember we're changing the y, so 5 minus 1 becomes 5 plus 1. So now let's find the slope. Remember that the slope is simply going to be the change in y, the rise, over the change in x, the run, or another way of saying it, y2 minus y1 over x2 minus x1. So in this case, y2 minus y1 is 1 minus 0, and x2 minus x1 is 5 minus minus 3. Now don't forget that subtracting a negative becomes adding the opposite, or so it becomes 5 plus 3. So our answer is 1 over 8. The interesting thing is that the original one was minus 1/8. When I reflect it over the x-axis, it becomes the opposite, or 1/8. Not perpendicular, just the opposite. 15 says if the figure is rotated 270 degrees counterclockwise about the origin, what will the slope be? Well, in this case, once again, let's figure out what the points are going to be. xy becomes y minus x, so they switch and the x changes. So A, the point A, 4 minus 5, if I turn them around, I get minus 5, 4, and then I'm going to switch the 4 to minus 4, so I end up with negative 5, negative 4. Y, on the other hand, switch them first, minus y, 5, and then the second one becomes negative, so negative 1, negative 5, and now we just simply do the slope. So the slope here is going to be y2 minus y1 minus 4 minus 5 minus minus 4. Remember, that'll be minus 5 plus 4, and then minus 1 minus minus 5, or minus 1 plus 5, and we end up with negative 1/4. Okay, so the slope of that is negative 1/4. Find y prime if it's translated using this rule. In this case, here's our rule. So I just simply plug in y prime. Y is 5, negative 1, so 5 minus 7, and y plus 2 is going to end up with negative 2, 1. Number 17 says find a prime if play is rotated using this rule. And so in this case, using this rule, which is actually a 90-degree turn, I put in the point 4 minus 5, so we switch them around and we get minus 5, 4, and then we take the opposite of the y, so minus minus 5, and we end up with 5, 4 as our answer. Number 18, what happens if I rotated 180 degrees around the origin? Well, a rotation is will it be congruent? I mean, a rotation changes xy becomes minus x minus y, but the question is it going to be congruent? And the answer is yes, because it's a rotation is a rigid motion transformation, and that means it preserves distance and angle measures, and so the figure PLAY is going to be congruent to P prime, L prime, A prime, Y prime. This is one of those questions you get on the test where they ask, you know, if I make this translation or this rotation as a reflection, is it going to be congruent? And the answer is yes, because it's a rigid motion. It preserves distance and angle measures. You just got to remember that phrase. For problems 19 and 20, they ask us to describe the transformation and write it in coordinate notation. In both cases, we're going from the dotted figure to the solid figure. The first one, as I look at there, I'm saying, how can I get the dotted at least oriented? And maybe I can orient it one way and then translate it that direction. So I realize that I can do that by reflecting it across the x-axis. So I draw my x-axis and then start reflecting the points. 4 down there, and then 4 down, and then 5 down, 5 down. And notice now I have the red triangle is in the same orientation as the black one. So the first part of my coordinate notation is my xy is going to become x minus y. Second part, now I just simply need to translate it for right. Now what I'm going to do with the coordinate notation, I'm going to use the first one and now simply add the 4 to the x. So you see I get xy equals x plus 4 minus y, and that notation combines both the reflection and the translation. On the second one, I look at it and notice, now how can I take the dotted and orient it? And I realize that if I translate it 90 degrees clockwise, which would be 270 counterclockwise, I can get in that shape. So let's do the translation, and that's the rotation, and that is xy goes to y minus x. Now you notice all I need to do is translate it 1 left and 5 up. It's a little tricky here. Remember that when you go to the 1 left, that's going to be the x coordinate -1, but right now y's in that thing. So notice when I write my final, it's y -1 and negative x plus 5, and that becomes the answer of that composition of those two transpositions. Problem 21 begins our constructions. First, we want to copy angle A. So the first thing we want to do is draw a line to be the bottom of our angle. So I simply draw there a point and a ray going to the right, and that's going to be the bottom of my new angle. Now I'm going to take my compass and put it on point A and draw an arc. It can be any size, but I just have to draw an arc across both rays. Then I pick it up and keep the exact same ray and put it on the point of my new ray and draw the same arc again. Remember, these arcs have to be the same length. Now we're going to measure our angle A. You're going to put your compass on where the red arc crosses the bottom, that point, and then figure out exactly where does it cross the other angle. We're measuring the distance across the red arc of that angle. Now if I come down and put it on my new angle and mark it again, you see I'm getting the same length. So now if I draw a line from my vertex through the point where they intersect, I have copied the angle. Now 22 asks us to draw a perpendicular bisector. Well, to do this, the thing about a perpendicular bisector is it cuts it in half, and there's a line where every point on that line is equidistant from the end points. And the way we do that here is first we're just going to draw a line, XY. Okay? So first thing we're going to do is copy XY. So that's pretty simple. Put your compass on point X and then measure Y and just make a little arc there and come down and put it on A prime and do it again. And now you see we have our new point A prime B prime matches X and Y. Okay. Now we're going to do the perpendicular bisector. So take your compass and go on point B and simply make an arc. It just has to be more than halfway across. Not farther. Well, it can be farther, but it can't be too short. It has to be at least halfway across. And then keep that same one and come over to A and do it again. Now the interesting thing is the 2 points where these arcs cross are each the same distance from A and B. And the line between them marks all the points that are the same distance. So if I draw a line between the two intersections, that is the perpendicular bisector. Problem 23 says do a perpendicular line to AB through point P. Well, we're going to start by simply going to point P, opening our compass, and drawing an arc through it. What we've established is the 2 points where they intersect are both the same distance from the perpendicular bisector that was going to go through P. Now take your compass again and put it on each of these points. Like if I put it on the point to the right of B and draw me an arc, take the exact same arc and do the other intersection where to the left of B, cut through, and now I have these two spots are equal distance from the red arcs. And now if I draw a line through there, I now have a perpendicular here to line AB at point P. Now we're going to do a parallel line. Well, the one unique thing about parallel lines is corresponding angles are the same. So we're going to use our ability to construct an equal angle to draw this. So first thing I'm going to do is I'm going to draw a line between Y and M. Okay? And now I'm going to I'm going to copy the angle at M and copy it onto Y. So just like we did a problem earlier, first I draw an arc on M, I come up to Y and draw the same arc. Okay? Now I come up here and measure, this time I'll measure from the top line, the length of this measure from where the intersects from there to there, and then come up and do it again on the top one. See, I'm trying to get the exact same angle. And now when I draw a line from Y through the intersection, what I have is a parallel line. And that is the construction of a parallel line. This one asks me to construct a line through point Y that is perpendicular. Well, I'm going to start by getting 2 points on either side of Y that are the same length. So just open up your compass and draw it, and Both sides are the same. I just need 2 equal points. Now we're going to take the compass, open it up a little bigger, put it on one of the, here I did it to the left of Y, and make an arc up there. Bring it with the same exact measure on the other side and mark it. And now I have these 2 points that are the equal distance, so I can draw the line through it, and that is a perpendicular to the point, through the point Y to the line M. This one is kind of fun. It says to construct a triangle using 3 given sides. There's lots of ways to do it, but let's start by, first thing we're going to do is measure the bottom side. So I'm going to put my compass, I'm going to draw a line, and then I'm going to put my compass on the bottom line and measure the length, come down to my line and measure the length again, and there's the end of my triangle. Now I measure the second one, and I come to either side, but I chose the left side, and I just mark that arc. Okay? That's the length of that side. And then we do the smaller side, do the same thing, come over the other side of the triangle and mark it this way. And notice I'm going to find the point where that length, the middle length and the smaller length intersect. And if I connect that point and that point, I've got my triangle with those 3 lengths. Problem 26 asks us to construct a rectangle with the given 2 sides. The unique thing about a rectangle is each of the angles will be 90 degrees. So you see we're going to have to create some perpendiculars for this one. Let's begin by creating the bottom. I'll draw a line, I'll put a point on it, and then I'm going to measure the longer side with an arc. Coming down the bottom, put my compass on the dot and mark the arc, and there is my bottom side. Now to get the sides, I just need to do perpendiculars. So if you remember how to do a perpendicular, we're simply going to go to one point and draw an arc one way and the other way, get 2 sides apart, and then we'll use the compass on either point and draw an arc up above it. So there's one there and the same arc above, and I'm finding the perpendicular so I can draw my line through there. I'll do the same over on the other one, the 2 lines, and then draw through. Now I have 2 perpendiculars. Now all I have to do is measure my side. So I come up and measure the shorter side, come to either point and mark that off, and there's a point, and mark it off the other one, there's a point, and now I have the 4 points of my rectangle, and I can connect it, and there's my rectangle with those 2 sides. Problem 27 is interesting because they want me to construct a 45-degree angle and a 22.5 degree angle. The key thing is to understand that 45 is half of 90. In other words, if I draw 90, which is a perpendicular, all I have to do is bisect it. Likewise, 22.5 is half of 45. So this is a problem of 3 points. Construct a perpendicular, bisect it, and then bisect it again. So let's start with a line, and we're going to draw a 90-degree angle. So I draw a point, draw 2 sides of it, and then put above it the blue, and now I've drawn my perpendicular. That's 90 degrees. So now let's take this angle and we're going to bisect it. So the first thing we do is take an arc across the angle. Now what we're going to do is we're going to take, we can even use the same arc, but we're on one side of the arc where it crosses. I'll make a mark up here and then go to the other side of where the arc intercepts and mark it again. And that point to the vertex is the angle bisector. So that means both of these 2 angles that I cut are 45 degrees. So I've drawn my 45-degree angle. I've actually drawn 2 of them. Now all I have to do to get 22.5 is do it the same to one of these other angles. So let's go to the smaller angle here in the bottom. And again, start where the red arc touches the bottom and make it an arc there, and then come up above here and make it again. That supplies that divides that in half. And so now I have a 22.5 degree angle. That's great. I hope you do well on your test.